Hello. So in this session we are going to revisit a topic that already we have discussed in the fundamentals of the subject, namely the reversible and irreversible processes. So let's define the reversible process. You know already, as the name suggests, a process is said to be reversible if the at the end of the process both the system and its local surroundings are restored to their own original states. Okay, or a textbook definition will be like this: a process that is performed in such a way that at the conclusion of the process, at the end of the process, both the system as well as the local surrounding, remember it is talking about the system as well as the local surroundings. It's not only the system. Okay, the immediate surrounding of the system should also be restored. It should be brought back to their own initial states without producing any changes in the rest of the universe. Means no change is actually permitted. Okay, even though we are focusing on the thermodynamic state of the system and the immediate surrounding, it has got also one more condition that it should not be producing any change in the rest of the universe. Okay, and already we have seen that all natural processes are irreversible in nature. We don't have even a single process which is not perfectly reversible. The reason also is well and clear, because in every process there will be some sort of dissipative forces and dissipative type of processes will be there. It will cause the dissipation of energy. So in all real process there will be some sort of dissipation of energy, either in the form of friction or viscosity or some electrical resistance, some magnetic properties and all. So due to that this is a very important thing that already we have discussed, that all natural processes are irreversible. Now if we want to attain, theoretically or ideally, if you want to obtain reversible processes, so what should be the conditions? So that is what is known as the conditions for reversibility. Okay, it's an idealization that will help us in just developing the theory. Okay. So there are two very important, or we can summarize the conditions for reversibility into two statements. So one is that the process should be performed quasi-statically. Okay, so you know what is the meaning of a quasi-static process from the very fundamental idea of thermodynamics. That is, the system must always be passing through states of thermodynamic equilibrium. Remember, it is thermodynamic equilibrium, which is a combination of thermal, chemical and mechanical equilibrium. The system is always in a state of thermodynamic equilibrium, and see that it is very near to at least thermodynamic equilibrium. And the second one is that there should not be any dissipative effects such as friction, viscosity, inelasticity. Other examples are also given for dissipative effects. Inelasticity, you know that usually materials are showing some property of elasticity, and there is some sort of inelasticity also. Beyond a limit it becomes inelastic. And electric resistance, if the systems are electrical in nature, then electric resistance is causing dissipation of heat energy or energy in the form of heat. Magnetic hysteresis, you have learnt about hysteresis curve and right, a BH curve or MH curve. Maybe you remember in your magnetism classes you would have heard of what do you call as see this sort of a curve, right? Okay, just like, or you can just take it now anyway. Okay, you see the shape of the curve was something like this. I hope you remember. Okay, so some sort of a curve like this, what is known as hysteresis. And you might have heard or remember that the area under the curve or area enclosed by the hysteresis loop is directly proportional to the energy lost during the cycle of magnetization and demagnetization. Okay, so magnetic hysteresis is also a sort of dissipating energy in the system. So due to all these, at least one form of this dissipative force will be, or dissipative phenomenon will be present in most of the systems. So we can say that we are not able to obtain a system which is devoid of okay, or these dissipative forces or dissipative effects. So that is the reason why we tell that all natural processes are see, theoretically they are what, irreversible, and reversibility is only an idealization. So having said that, we will just discuss some of the examples. So any process which do not satisfy the definition of a reversible process is known as what, an irreversible process. You will be able to distinguish that. Okay, so if the system and the local surrounding is not restored at the end of the process, then that process is known as what, irreversible process. Okay, so where all this okay, the reverse conditions of reversible process will be always exist. Okay, so now our example, okay, or we will just discuss, okay, some examples of irreversibility, because that is the natural thing that is happening. So if you want, you can just discuss what is known as what are the features of irreversibility. You can see that the features of irreversibility will be just what, okay, related to the condition for irreversibility, the condition for reversibility, right? Features of irreversibility will be related to the condition for reversibility. The violation of the condition for reversibility will be the feature of our irreversibility. Okay, so let's see one by one. See the conditions for mechanical, thermal and chemical equilibrium, namely the thermodynamic equilibrium, are not satisfied. So these conditions are not satisfied. That is the first thing to be taken care of. And the second one is that dissipative effects such as friction, viscosity, inelasticity, electric resistance and magnetic hysteresis are present. Either one or several of these are present in the system. Now in order to learn about irreversibility, or we are trying to classify the irreversibility into several categories for ease of study. Because this is a reality and reversibility only is an idealization, as I was repeating several times. So let's classify the irreversibility into three categories. Okay, because you have already seen that the feature of irreversibility is that the condition for mechanical, thermal and chemical equilibria are not met. Okay, so if any one of these conditions is not met, then we can say that there is no any thermodynamic equilibrium, you know. Okay, so irreversibility can be due to pure mechanical reasons, or due to pure thermal irreversible reasons, or due to pure chemical, or a combination of all the three. Okay, so if anyone is not okay, just satisfied, then you know, okay, we will call that one as what, an irreversible process. Right. So now further, if you say this mechanical irreversibility can be further classified into external mechanical irreversibility. So this only for the ease of learning, external mechanical irreversibility and also internal mechanical irreversibility. Internal mechanical irreversibility. Similarly, if you want, you can just discuss this one also. Thermal also into external and internal. Thermal, external thermal irreversibility and internal thermal irreversibility. Okay, so this is just depending on whether the heat exchange is happening between the system and a surrounding, or in between within the system, within different parts of the system. Internal means, you know, intra, within different parts of the system. So chemical, of course, you know, you need not classify as external, internal and on. So that is a different types of irreversibility. See, only for the sake of just clarity, we will discuss some of the some of these examples of irreversibility in detail. Okay, so let's do that within some some time. So let's go to the examples of external mechanical irreversibility. Remember, it is mechanical. I told you, out of the three, mechanical, thermal and chemical, we are talking about the mechanical irreversibility first. Okay, so there are several examples for the external mechanical irreversibility. See, we are classifying these examples into two categories. Okay, so the first category is this one, in which there will be an isothermal transformation of work. Okay, where internal energy of a reservoir remains unchanged. The internal energy of the reservoir should remain what? Unchanged. And there is an isothermal transformation of work. Okay, so you know what is my isothermal transformation of work, because the temperature should be remaining T is equal to a constant. Okay, so let's see how it's happening. And I have given some examples. These are some standard examples taken from your reference textbook, Zemelsky. And each of this example will be just related to one form of the dissipative force. Okay, hope you remember which are the dissipative mechanisms. It can be friction, it can be viscosity, it can be inelasticity, it can be electric current, it can be magnetic hysteresis, right, depending on the system, right? So any one of these can be a reason for the irreversibility or dissipation of energy, right? So the examples, you can just read some examples, specific examples. Okay, what are specific example? Friction from rubbing two solids in contact with a reservoir. I hope you remember. We began our discussion of this module by explaining what happens if you are rubbing two stones underwater, right? We are rubbing two stones in underwater. So what happens there, that you are doing some work, okay? As and when the work is done, the stone may get heated up, but the heat energy obtained or produced during the rubbing of the stone will be automatically, okay, or suddenly it will be getting conducted to the water. So if you are rubbing two solids in contact with a reservoir, you can see that the temperature of the solid will not change, right? The temperature of the solid will not change, means temperature of the stones can remain the same. So that is why we told that you can convert work completely into heat. That is of course permitted. 100% conversion is permitted, or it is theoretically possible, right? That type of process is what is known as isothermal transmission, because the temperature of the system is not permitted to change. So the temperature T is equal to a constant. Remember here in this example, the system means what? The solids, right? The solids in our specific example, it was the stones. So friction is present there, okay, right? Friction is present there. That's it. Now, irregular stirring of a viscous liquid. Irregular stirring of a viscous liquid. Remember, you note this particular point: viscous liquid. That also in contact with a reservoir. Okay, in every example what is cited here, you can see that it's specially mentioned it is in contact with a reservoir. Okay, I'll tell you what is the importance of that one. See, the third one is inelastic deformation of a solid. Yeah, suppose that you are deforming a solid by making it stressed. Okay, so it is just what do you say, that you are deforming it beyond the elastic limit, then it becomes an inelastic deformation. Okay, you are stretching, or you are just giving stress to any solid object beyond the elastic limit. It will be undergoing what is known as an inelastic deformation. Then in the case of electrical systems, a transfer of current through a resistor. Okay, so if you transfer current through a resistor, or in the case of magnetic system, there is a magnetic, you perform some cycles of magnetization and demagnetization. It will be undergoing a process what is known as a phenomenon will be there what is known as magnetic hysteresis. Okay, so all these are some examples of irreversible external mechanical cases. Okay, so let's discuss it more elaborately. So this is a general representation of all these examples. So all these five specific examples can be represented by a single block diagram. This is what so let's see what is happening. For example, I can take the first example. Okay, this example I am taking. See, so system here means the stones. So example stones, rubbing two stones. Okay, so we are doing some work, right? We are doing some work. So work is done. That is why the arrow has been shown to be enter. Okay, so what happens? The stones are just rubbed together. So the heat is produced. Is it not? Heat is produced. So some Q amount of heat is produced. Right? Suppose that I am doing some 100 joules of work. Right? Then it produces 100 joules of heat. Now the condition is that the temperature of the system should remain constant. So how is it possible? It's possible if the system is in contact with a heat reservoir, right? If the system is in contact with a heat reservoir, a big reservoir, okay, have very large specific heat capacity, what can happen? The 100 joules of heat, whatever is obtained in the system can immediately be transferred to the heat reservoir. So the 100 joules of heat is now getting transferred. That's why it is shown that, okay, in the arrow Q is transferred. That Q will be equal to the W that was performed. So 100 joule of heat is entering the system, and immediately the 100 joule of heat will be just given off to the heat reservoir, right? So what about the change in state of the system? So the change in state of the system, UF, it's the final internal energy, and minus the initial internal energy, that is delta U. So delta U is equal to 0 in this process. There is nothing wrong. Okay, feel that the system has undergone a thermodynamic process where there is no any change of state of the system. We feel that the process is what the process is what you can say reversible. But think of the thing. So what is our definition of reversible process? It's not only the system, but the immediate surrounding should also be remaining what? Without any change. But here that the surrounding is what you call as the heat reservoir, right? So this is the role of immediate surrounding, right, in our statement. But here, even though the system has got no any change of state, the surrounding has got some increase in its heat, right? Increase in its energy, I can say. Okay, so it's 100 joule of energy more. So certainly the internal energy of the heat reservoir would have got increased, okay, by 100 joules of energy. So let's argue in the reverse sense. It can be if you have to restore the system and its local surrounding to their initial states without producing changes anywhere else, what can happen? You think of that, some 100 joules of heat energy, because there is a large amount of heat energy here. So 100 joules of heat energy, let me say that Q amount of heat energy is extracted from the reservoir, and it's completely converted back into work. If this is done, there is no problem. Why? Because there will be, once again, delta U will be equal to 0 for the system, because 100 joule of work has been extracted from the heat reservoir, and it is completely converted into work. There is nothing going to change as far as the system is concerned. Okay, if such a thing is happening, you can say that the system is not affected at the end of the cycle, and reservoir immediate surrounding is also not affected, because it has come back, right? Seemingly we will say that yeah, it's okay, but there is a great problem here now. Why? Because you can see what we have discussed now. See, 100 joule of heat is taken from the reservoir, and it is completely converted back into work. Is not that now a heat engine is not the function of a heat engine whose efficiency is equal to 100%, and we have seen that there's a clear violation of the second law of thermodynamics. So it violates, this particular argument violates second law of thermodynamics. Okay, and hence we can say that in all these examples, one way the process can happen, but for the system and the local surrounding to be just left with no change, the reverse should happen. The reverse should happen means it will be just a direct violation of the second law of thermodynamics. So hence we can say that all these examples represent what is known as external mechanical irreversibility. Why we say that it's external? Because it is the system in all these examples are in contact with an external reservoir. That is why we call these examples are external mechanical irreversibility. So now, having discussed these examples, let's we will discuss some examples of external mechanical irreversibility. We'll just discuss another category of another discussion. Here it was isothermal transformation. and we will discuss another case where there is adiabatic transformation. Okay, these are some examples. We'll just see. Okay, right. So next set of example, this is also external mechanical irreversibility. In this set of examples, we'll see the transformation is happening not under isothermal condition. There is no any reservoir that is associated, but it's under adiabatic conditions. Okay, so in order to specify that is the adiabatic condition, you can see that the system now has been shown thermally insulated, so by some adiabatic walls. So these lines or these walls are adiabatic in nature. These are adiabatic walls. Okay, now let's see what are the examples. So you will see that examples are very same. Okay, almost the same. Friction from rubbing of two thermally insulated. See that the word has now changed, thermally insulated. So everything earlier it was in contact with the reservoir. Now every example that we have discussed earlier now has been just converted into thermally insulated systems. Okay, so other things are same, friction, okay, viscous thing, then inelasticity, then there is what electric current, then there is a magnetic hysteresis. Examples remain the same, 5 typical examples. Okay, so here what happens is that, you know, whenever you are doing some work on an thermally isolated system, okay, you automatically know that there will be a change of temperature from some Ti to Tf. The temperature of the system must change, you know, because it's thermally isolated. Okay, so it will result in a change in the internal energy also. You can say that the initial internal energy is Ui, that changes to some final internal energy Uf. So such that we can say that the work done W will be equal to the final internal energy minus initial internal energy. You know that internal energy is a state function, Uf minus Ui. So a process of this particular type is accompanied by a rise of temperature of the system. Okay, and the internal energy is changed by some delta U. So we say that is equal to delta U. In our earlier example, a set of examples, delta U was equal to 0 because the process was isothermal in nature. Okay, now so I can say that this delta U has been the change. There's a change. Now for this process to be reversible, what should happen? This delta U should be restored. Okay, means whatever increase in the internal energy should be what? Reduced by the same amount. For that, what can be done? In principle, what can be done? Suppose that this much of delta U is not, if this much of delta U is okay, extracted in the form of heat. If this much of delta U is extracted in the form of heat, then automatically what will happen? The temperature of the system will be just dropping from Tf to the initial value Ti, so that the state of the system is now it's just restored, right? And in this process, this heat, okay, no, this heat has to be completely converted into work, and you know that's a clear violation of the second law of thermodynamics. Some heat is drawn from the system, it is completely converted into work, means this is a violation of the second law of thermodynamics. If it is not done, the process will be irreversible. Okay, there will be change in the state. For having no change in the state, you should be able to perform something like this, but the second law forbids that, or it restricts this particular convention. So we can see that this is an example of another example of what you can see, external mechanical irreversibility. Similarly, you can we can say that wherever there is a process which involves the dissipation of work into internal energy, they are exhibiting what you say the external mechanical irreversibility. Okay, so already we have mentioned about what is known as perpetual motion machine of the third kind. You know that see all those machines, okay, which in which there is no any heat dissipation, or there is no any dissipative forces, are said to be what is known as a perpetual motion machine of the third kind. So you know, I told you that it's a hypothetical machine, there is no any real perpetual motion machines. Now if you want something what is known as Internal mechanical irreversibility, there are some examples. The examples are some ideal gas rushing into vacuum, that is known as free expansion. Ideal gas rushing into vacuum is known as free expansion. We will discuss about free expansion in the next module in detail when we discuss what is known as the concept of enthalpy. Okay, we'll just do that one later. Similarly, the example of gas flowing through a porous plug. You might have heard about this one, that's known as porous plug experiment, or it's also known as the throttling process or Joule-Thomson expansion. This is a technique that is used to produce low temperature, okay, in the cooling of gas and all. We'll be discussing about Joule-Thomson expansion and Joule-Thomson coefficient also later. We have discussed Joule expansion earlier, but this is Joule-Thomson expansion, a bit different. Then snapping of a stretched wire after discard, collapse of a soap film after it is punctured. All these are some examples of internal mechanical irreversibility. Okay. So in all these cases, first the energy transmission is taking place as a result of the mechanical instability, and then energy is transformed into internal energy by virtue of some dissipative effect. So okay, these are just only for the sake of completeness. We are discussing all these examples. The matter is that you should be able to understand that all the naturally occurring process or all the natural processes are basically irreversible in nature, and reversibility is only a theoretical construct. Now we'll have see external and internal thermal irreversibility. Okay, so in the case of thermal irreversibility, you take the external first. External case is conduction or radiation of heat from a system to a cooler reservoir. Okay, you know that heat always flows from hot to, is it not? Hot to cool, is it not? Hot to cool, that's a direction of flow of heat. So once this thing has happened, the reverse process is not happening. Okay, the state of the system and the surrounding will be remaining unchanged only if from the cooler body heat is flowing back to the hotter body, but that is a direct violation of what you say, that the second law of thermodynamics. So that's never occurring. Then conduction or radiation of heat through a system which remains unchanged from a hot reservoir to a cooler one. Okay, so these all cases, so hot reservoir to a cooler one, that also that is happening through a system. That's the only thing. Okay, just you have a hot reservoir. Okay, some heat Q is there. There is an intermediate thing, what is known as a system, and this is actually then it is what flowing through under a cold reservoir. That's the thing. So in this case also heat is just flowing, the system becomes an intermediate thing. So like what happens is that for the reverse thing to happen, that the system will be having a lot of dissipative effects, so automatically you won't be able to convert completely back into the thing. So that will be just to see that the back conversion will be always affected by the second law of thermodynamics. Okay, so that is known as the external thermal irreversibility example. So if you want the internal thermal reversibility, you consider the heat transfer between two parts of the same system, so from one part of the system to the other part of the system and vice versa. Then that is what is known as what the internal mechanical internal thermal irreversibility. And this type of how can this type of a heat transfer occur? It can happen due to some non-uniform temperatures. If there is a non-uniform temperature non-uniform temperature distribution across an object, then such a type of heat transfer can occur. And that is or you can say that if there exists what is known as a temperature gradient, so that causes what is known as what that is an example of the internal thermal irreversibility. Now similar manner we can talk about chemical irreversibility. So the processes that involve a spontaneous change of chemical structure, that is chemical structure can be changed, density can be changed, phase can be changed. All these processes are just showing what is known as chemical irreversibility. So we can have some examples. Formation of new chemical compounds. Okay, so all chemical reactions, okay, are an example of chemical irreversibility in the formation of new chemical compounds. Okay, so maybe the reaction is reversible, but always we can see that there will be some change that is left. Okay, the reaction may be coming, but okay, coming back to produce the reactants, but maybe some amount of heat is liberated. Okay, there will be always some difference in the physical properties. Okay, now mixing of two different substances, diffusion of two dissimilar inert gases, mixing of alcohol and water. These are some specific examples that stated. Sudden change of phase, freezing of supercooled liquid. So what is that? I mean, supercooling, you would have heard of that one. So if you lower the temperature of a liquid or a gas below its freezing point without it being solid, okay, so due to the absence of what is known as nucleation sites, it becomes what is known as supercooled. Especially so you would have heard of formation of clouds and all that, cumulus clouds and all. Okay, so it's actually supercooled liquid phenomenon, vapor is present there. Now condensation of supersaturated vapor. Okay, that's what is happening actually in the case of cumulus clouds. Now transport of matter between phases in contact, solution of solid in water, osmosis. All these examples are showing the chemical irreversibility. See that to summarize, this is the thing that all processes, naturally occurring processes are actually irreversible, and basic reason for irreversibility is due to the presence of some sort of what? Dissipative forces. Like 5 of the common dissipative agencies we have identified. It can be friction, it can be viscosity, it can be electrical resistance, it can be what? Magnetic hysteresis, or it can be some sort of inelasticity. Okay, so now maybe we'll think why we are just talking about what is known as reversible process, even though it is impossible, because we cannot satisfy the conditions for reversibility. A reversible process is purely an ideal abstraction, but it is extremely helpful in theoretical calculations. Okay, that's fine. Now we will be discussing about what is known as the Carnot engine. Okay, because we already discussed about what is meant by reversibility, what is meant by irreversibility, what causes the difference. Now we are in a state to discuss the most ideal type of heat engine in theory, what is known as the Carnot engine. That we will do the next session. Okay, so you read on this particular topic. I had already given you this topic as some reading assignment. It's only to give you a background knowledge about the nature of objects and nature of the different processes. Thank you.